Log on, tune in, find out. Another good idea from Cambridge.
This is Nitin Nitsure from the Tata Institute in Mumbai, and he will speak on deformation theory.
I begin with thanking the organizers for inviting me to this program. 3 lectures is a very small number of lectures for a subject like this, but I have made my notes available, and they are on the conference. Can you hear me, Steve?
Can you turn it on?
I turned it on.
Is the red light on?
Should I begin all over again? Okay, I said thank you to the organizers, and I also complained that 3 lectures is a short time for a subject like this, but I have uploaded some notes on the conference web page, which are more systematic than what I'll do here. Introduction to the infinitesimal aspects of deformation theory for coherent sheaves. What I'll do here is an overview of the entire algebraic approach to deformation theory, and therefore I won't be able to go too much into details, but of course during the tutorial hour we can talk in greater detail. So let me begin with some history in the form of some names. Modern deformation theory began with Codera, Spencer, around 1958, and they worked in the analytic category. Soon Grothendieck began his algebraic program of developing everything that they did in his new language of schemes. And so the names are Grothendieck, Schlesinger, Illusi, and Michael Artin. These are the main names associated with the theoretical development of the classical algebraic approach. There is also a modern algebraic approach currently under development by people who talk about homotopical algebraic geometry. Okay, so this is starting around 1960 or so. Schlesinger about 1965, Illusi around 1966, and Artin in a period culminating in his 1974 paper. This is the paper called Versal Deformations and Algebraic Stacks. This is Invenzione 1974. Now all Google search is very easy and you have MathSciNet, so I have not bothered to write precise references which you can easily find. Now much of the technology of abstract algebraic geometry found use in this. In fact, lot of it was developed in response to problems of deformation theory. For example, Artin stacks were introduced in this paper to solve deformation problem, and Grothendieck, right from his very early attempts to convert Codera, Spencer into algebraic geometry, had to use functor of points, had to use nilpotents, and had to use formal schemes, and much of the technique of FGA goes into this kind of a thing. Schlesinger developed the infinitesimal theory for functors on Artin rings, but there was no good calculus to produce to solve the problem of deformations one infinitesimal step at a time, for which the machinery was the so called cotangent complex. And this cotangent complex was first started off by Grothendieck, who realized that for schemes in general over something, which are not smooth. The Kähler differentials are not enough, and what you really need is some kind of a complex. And he developed a one-term complex, 0 and 1. And then Schlesinger and Lichtenbaum developed a two-term complex. Then Andre and Quillen developed it in commutative algebra all the way, and Illusi did it over schemes and more generally over topoi. And so that development culminates in this thesis of Illusi, 2 volumes, complex cotangent 1 and 2. Okay. Much of it is very difficult to read, at least for me. And then Artin found that most of the deformation problems that were considered had the characteristic that the objects had automorphisms. It was not enough to simply consider their isomorphism classes. After all, as you know, to make a vector bundle on a space, you have some trivial bundles on open cover, and in the overlap you glue them. For that you need an actual vector bundle to glue. If you just look at its isomorphism classes, the isomorphism class is trivial, and so you cannot produce a vector bundle by gluing isomorphism classes. You have to produce a vector bundle by actually gluing it using automorphisms of that bundle on the overlap. So automorphisms are extremely important in this subject, and you lose them if you consider functors which take values in sets, which was the style up to then. In GIT and everywhere people were considering set valued functors. So Artin realized that you have to carry groupoids with you all the way. Before Artin, somebody else realized that, and that was DS Rim. Rim took what Schlesinger had produced and recast it in the language of groupoids, and this is in SGA 7.1. All right, so this much will do for history, because much of the history begins to make sense only after you understand some of the technical issues somewhat, and I have seen some examples. And in 3 lectures I cannot systematically give all definitions and develop the subject the way it should. Instead, I will focus on 1 or 2 key examples. These are the simplest kind of examples, but designed to bring out the theoretical issues. It's like, and what many of you will need to use deformation theory. Many of you might have already used deformation theory in your work in algebraic geometry, and there you need rather clever tricks and techniques, because these lectures are like explaining the Riemann integration theory and the Lebesgue integration theory, and then you have special functions of modular form, and you need to evaluate some integral, and all your knowledge of Riemann integral is useless in trying to do a particular difficult integral. So there is a science to it, there is an art. So as far as these lectures are concerned, I am going to just lay out the sketch of the basic theory, and when it comes to applying it to something of interest, you will have to supplement it quite a lot by detailed knowledge of the situation in which you are going to apply it and make clever tricks. So these lectures are not going to equip you to go and start doing deformation theory of the kind of objects that you want to deal with. Okay. So let's begin. So what is a deformation? In very naive terms, you begin with some object which you want to deform, and you produce a family of objects parameterized by some space, and this is a pointed space at some particular point. This ET0 is isomorphic to E, but not just isomorphic, you have to give an isomorphism, given isomorphism. This is because things are automorphisms, as you will see. So such a family of objects, whatever family means, and you have seen various descriptions of families, or augmented bundles, principal bundles, all kinds of things you have seen what are families. So, family in whatever sense and parameterized by space, whatever that space means, that is what is a deformation. So, to give some examples, you might begin with a 3 manifold with a Riemannian metric, and you want to follow a Ricci flow and deform the metric, and you hope to make it round. Or okay, that is not very easy, and that is outside algebraic geometry. So, forget this first example. Let us give another example. You might want to intersect 2 plane curves and count the number of intersections, and then you know you can deform each one of them into a union of lines, and then take the intersection of the lines and count it. So, this is a very global deformation going a long way. Or to talk of it locally, suppose 2 curves are intersecting and the intersection is bad, you might want to deform one of them till the points become separated and simple. So, all these are examples of deformation. There are examples in number theory where you might have something over a finite field and you want to lift it to rational numbers or some number field. So, this will be deformation theory done over with vectors as your base, and this is one of the key ingredients in the proof of Fermat's last theorem. So, there will be all kinds of examples. E may be a scheme, a Galois representation, a vector bundle, a coherent sheaf, any object, almost any object which occurs in algebraic geometry. Now, often this T, the deformation space, is to be thought of in a relative sense. So, from your experience of algebraic geometry, you know you have to study things in a relative situation. So, there is a base space S and some base point there S0, and when you think of deformations, you think of the parameter space mapping to this and this point going there, and the deformations are parameterized over T. The way to make these deformations is you begin with the starting object which you regard as lying over S0, and then you try to spread it to a neighborhood, and then you try to spread it to a bigger and bigger neighborhood, and ever larger neighborhood as much as possible. And then you want to know whether you can do it, what are the obstructions to doing it. You want to be able to calculate how many extensions are there, is there an extension or not, and then what is the maximal possible such extension which has some kind of universal property. Now, I will again characterize what kind of universal property in due course more precisely. So, by doing it right, you end up with a deformation which is maximal in some sense, what is known as versal deformation. And these versal deformations you can produce in good cases starting from each one of the points of S. You can produce such a versal deformation, and then these versal deformations you can somehow glue up together and produce a moduli space. So, the final aim of all this deformation theory is to produce moduli spaces by a method which bypasses GIT and can sometimes work where GIT does not work, because GIT needs projectivity all the time. On the other hand, GIT can produce better results because projectivity indeed gives you powerful results. So, the aim of deformation theory is to begin with individual objects like vector bundles, varieties, whatever, deform them more and more, produce some kind of maximal families of deformation centered at your starting variety, begin with another starting variety, produce lots of these families and glue them together. Now, when the issue of gluing these together came up, Artin realized that the gluing can't be done in Zariski topology. So, he had to do it in étale topology. Often he could get away by doing it in étale topology, and that is what led to algebraic spaces. Later on, when he tried to do this gluing, he found that even étale topology is not enough because they are automorphisms, and then the way out was to so glue these deformations as to produce a stack. Next week there is going to be a course on algebraic stacks. So, the few remarks I will make out algebraic stacks can be better understood after the next week, but of course, we can always discuss during the tutorial hours. Okay, so this is some kind of overview, and now let me begin with a very concrete problem. So let's begin with vector bundles, and the idea of deformation theory is to spread a starting object to a little neighborhood. Smallest possible neighborhood schematically is one where the square of the defining ideal is 0. So let's think of the following situation. X is a scheme, is a closed subscheme, and there is this ideal sheaf with I square equal to 0. Okay. This is defined by the ideal sheaf I in OX prime, and because I square is equal to 0, I is an OX module, okay, quasi-coherent. Okay. Now suppose I have a vector bundle on this. Here is a vector bundle on X, and I want to produce a vector bundle on X prime which prolongs E in the following sense. What I want here is a pair E and I where E is a vector bundle on X prime and I is an isomorphism of E with E restricted to X. So we can ask basic questions. Does such an E exist? When it exists, how many of them exist? And for any one of them, what are the automorphisms? Remember these three questions. These three questions will come up again and again in the infinitesimal part of deformation theory. When is it possible? What is the obstruction? How many? And what are the automorphisms? So to answer these questions, let me to begin with make simplifying assumptions. So assume, later on I will get rid of this assumption, that rank of E is 1. So I will call it L instead of calling it E, and assume moreover that H naught So I am making this simplifying assumption that, can you see this up to here, up to where? All right, yeah, I hope this is visible. So I am making two simplifying assumptions. One is I am in rank 1, and second assumption is that global sections, invertible sections, surject to global invertible sections. Of course, this happens locally, but I am assuming it happens globally. So under these assumptions, I have this short exact sequence. This is taking a function on X prime and restricting it to X, and the ideal gives you invertible functions by anything 1 plus f into 1 minus f is 1. So 1 plus f is invertible. Anything nilpotent will do here. So this is a short exact sequence of sheaves, and look at the corresponding long exact sequence. So H0 to H0 being surjective, it will produce an exact sequence H1 xi to if you are puzzled why I write x here, please remember that I square is 0. So, the sheaf I is really on x. Okay, so the answer to the 3 questions is going to be 1, if Li is an extension also called lift of L to x prime, then ought the automorphisms of Li is going to be equal to H0 xi. Okay, this is clear.
Maybe you take x bar of x prime in the second part of the law extension.
This is a
When you take h1 of x prime over x prime, why is it x prime
the topological space is the same. X prime is x, only the sheaf is different. Yeah, this is an infinitesimal extension. The point set theoretically or topologically, there is no difference between x prime and x. You know, x prime has an infinitesimal thickening. It has some extra functions, and those extra functions times any other such extra function 0. Square is 0. Okay, so automorphisms of this are H0 xi, because if I take any automorphisms, it is supposed to preserve I. Therefore, it is of the form 1 plus f, where f is in I. The answer to the second question a lift exists if and only if, let us call it here, and now L defines an element there, and then there is so these are infinitesimal automorphisms. This is where the obstruction lies, because suppose something goes to 0 there, and then it comes from here. You have some line bundle L prime, which restricts to L on x, and 3 the set of all lifts is a principal set, possibly empty, under H1 xi. Two things coming from here will give the same lift, preserving I. So, I have so arranged this first example that everything can be read off from such a long exact sequence. But now let us do it in full generality, where E is of arbitrary rank, and I do not assume this anymore. Okay. So, this I have said it in the simplest possible terms, because you are already familiar with these long exact sequences and the Picard group, and you can verify these statements as 2-line exercises. But let us go to the situation in full generality, where I will give all details, where rank of E is arbitrary, and I do not assume that anymore. For simplicity, I will assume x is separated. This assumption is not a must, but simplifies calculations, because otherwise one has to replace check coverings by hyper coverings and lot of bad notation. Okay, so let us talk of it in full generality. So, there let UI be an affine open cover of X such that E restricted to UI is trivial. Choose a trivialization. and you know that ui intersection uj is again affine by separatedness. And so this affine open cover can be used to calculate cohomologies of coherent sheaves. Now, how does one describe E itself over this affine open cover? By transition functions. Gij with respect to the chosen trivialization. Okay. So, now we can write transition functions. Now, we want to prolong the vector bundle to x prime. So, what should you do? You should find some transition functions over x prime which restrict to the given functions on x. So, we want to prolong Gij. A little point I should probably explain here. If your vector bundle is trivial on ui, and now ui defines an open subscheme of x prime also, as I said, x prime is the same topological space as x, and so ui is also open in x prime. Consider the corresponding open subscheme of x prime, call it ui prime. So, ui prime modulo the ideal I is ui, but as open sets they are the same. Now, if your vector bundle is, suppose it admits a prolongation and it is trivial on ui, then of course, it is trivial on u prime I, and you can choose a trivialization which prolongs the trivialization on ui. That is because ui is affine. So, u prime I is also affine. So, these are little points which you are probably aware, some of them are exercises in Hartshorne. And so, now I want to prolong these transition functions. Will this be possible? What should I do? And if at all it is possible, is it possible in many ways? So, one of the interesting things which perhaps all of you have noticed is, if I take Gij and add to it Hij, and these should belong to I, and I try to check for the cocycle condition, then I end up getting Hij Gjk plus Gij Hjk is equal to Hij. This simply means that Hij is a cocycle in okay. You might think, why not this? But that is because the basis is changing all the time, and if I want to express the cocycle condition with respect to common basis, and here the common basis is the sending basis is from uk and the receiving basis is from in ui. So, you want to adjust all your matrices to go from the same basis to the other same basis, and then you can compare. So, this is just the cocycle condition. So, given any, if I have any such cocycle and I begin with an extension already and add Hij to it, I will get a new extension, and these two new extensions will be isomorphic if and only if the cohomology class of Hij is the same. So, these are simple check cohomology calculations with local trivializations, and they tell us that the 3 vector spaces that we are looking for. So, first possibly empty under also automorphisms of any extension because for such an automorphism it should restrict to identity on X, and therefore it should, when you subtract identity from it, what remains is an element which vanishes on X all along, and so it is a section of I tensor end E. Okay, so these 2 statements are clear. The interesting statement is the third one, which I will now prove. That says that the obstruction let us find out how. So, suppose I have been given this cocycle G I j and I want to extend it. So, I am looking for G prime I j. So, the way I can manufacture a vector bundle is on each of these u prime I choose a trivial bundle, and this is u prime j, and I choose an arbitrary gluing between them which extends the gluing G I j. Therefore, I will arbitrarily put G prime I j, I will put it to be equal to G I j plus X I j. Okay. Now, suppose I want to know by how much this equality fails. I want to know whether this holds and by how much it fails to hold. If it fails to hold, by how much it fails to hold. So, for that, if I write out these equations, and this belongs to I. All right, I think I should not write it in this form, but straight away I should simply, okay, I shouldn't write such an equality because it does not make sense. This is in one and this is another. So, I want to know whether this holds, and for that I should compare the 2 sides, and the way to compare these 2 sides is to simply subtract one from the other. So, I will put Cijk is equal to this would be 0 if I already had a cocycle. What I want to know is this 0, and all that I am assuming is that G prime ij restricted to Uij is Gij. This is all that I need, and I want to know whether this is 0 or not. Now, just from its definition and the fact that Gij times Gjk is equal to Gik, this and this, take these two and you can verify that the following equality holds: Gij Cjkl minus Cikl plus Cijl minus Cijk Gkl is equal to 0. So, 1 and 2 give you this equality 3. There is a tutorial hour coming up, and if you want to know how, that will be shown then. This is my way of acquiring some extra time. Okay. So, what does this equality show? This equality is about linear transformations where the sending basis is from UL and the receiving basis is in UI. In these terms, this equality says that Cijk is simply a 2 cocycle in U I tensor and E.
I'm a bit confused
Yeah.
what equation 3, what it says.
Yeah.
The
This-
Cijk are living in OX prime.
This simply is the boundary of C. How do you find the check boundary? So, you drop one index at a time and take alternating sum. So, you would think the boundary is Cjkl minus Cikl plus etc. But remember, these are endomorphisms. So, you cannot simply add and subtract them unless they are in terms of the same pair of bases. So, to compare two endomorphisms from one vector space to another as matrices, you need to have common sending basis and a common receiving basis for both of them. So, the transition function is put in to make the receiving basis always I.
I have an even stupider question, which is just,
Yeah.
Cjkl looks to me like it's, sort of a matrix over OX prime,
Right.
and you're multiplying it by the Gij.
Yes, but yeah, therefore, these are all matrices. Like Hij are matrices here.
I mean, OX is a quotient of OX prime. How can you multiply things in OX prime by things in OX? That's the source of my confusion.
Sorry. What do you think one can multiply with?
How do you multiply an element of a matrix coefficient of Gij by a matrix coefficient of Cjkl
This is a matrix.
with coefficients in OX, right?
No, this is just a matrix, plain matrix solute function. That's all. Gijs are simply matrix solute functions, GLN valued functions. Whenever we talk of transition functions for a vector bundle, it's a matrix of, say, holomorphic or regular or whatever functions. So, these are all matrices. This is also an n-by-n matrix. This is an n-by-n matrix. Everything here is an n-by-n matrix. And the I, J, etc. Refer to the open cover. They are not the matrix indices.
Are the C's in I?
Huh? Yes, C's are in I.
I,
Correct.
Because
because of the equality 1, 2 says that the difference is in I.
That's
So
why
these are matrices in I. Yes. Maybe that's what.
Yeah.
Okay. All right. So therefore you get this cocycle. Now suppose this cocycle was a coboundary. Suppose this cocycle Cij was equal to boundary of some xij, let's suppose. This equation written in matrix terms will read something like Cijk is equal to Xijjk minus Xik plus, I might be making sign mistakes, but okay, Gij(xjk). This is what it's being a boundary in matrix terms will mean this. And once that happens, so unless I have made sign mistakes, once that happens, G prime ij minus xij times G prime jk minus xjk will be equal to G prime ik minus xik. This equality will be satisfied if this equality is satisfied. This can be rewritten like that. So if this C is indeed a cocycle, which is a coboundary, then you can correct it by subtracting something whose boundary is that and get a cocycle. And these are again in I. Therefore, this again restricts to Gij on Uij, so this is the desired prolongation. So, let me recapitulate. The way we made the prolongation was take an affine open cover which trivializes E, and on each one of those open sets choose the trivial extension which always exists. Glue this together by arbitrary functions G prime ij, which just prolong the functions Gij, which is again possible. But this new G prime ij will no more be a cocycle in general. The failure for them to be a cocycle is measured by this difference, which otherwise would be 0. But this difference is actually an element here because of this equality. Okay, this is the boundary of C. And therefore, it defines a certain cohomology class. That cohomology class is the obstruction. If that cohomology class is 0, then there exists some Xij which satisfy this equality, and this equality will imply that this cocycle condition holds, and so you get an extension. This is the argument. This argument in check form, okay, you have to do it once, but the same argument occurs again and again. And really what is behind this argument is all possible such extensions on open sets form a gerb in the Zariski topology on X, and this gerb has the band or Lian I tensor end E. So this kind of problem arises again and again where there is a gerb with a certain abelian band, and you want to know whether the gerb has a global section, and that is given by a second cohomology class. Okay, so this is an example of that. We will continue to see examples of this all the time. Okay, so this took longer than what I imagined. So let's look at a second problem. This was the first problem. Let us look at a second problem. The second problem is really one of the fundamental problems of deformation theory, because a whole lot of other problems can be reduced to it or variations of it. This is the problem of deforming a scheme itself. Not scheme is given and a sheaf is to be deformed, but now you want to deform a scheme itself. So in its simplest form, what you have is you have some ring A and some quotient of it. Let's suppose that I square is equal to 0. And so, in schematic terms, I have spec A, and inside that I have spec of A mod I. And what is given here is a certain scheme. Let's call it S0, and this is flat morphism. And what we want is a Cartesian diagram such that this is flat. So this is a problem of prolonging the scheme itself from a given base to a larger base. The way such a problem can arise, for example, is I might have something like, say, Z mod 4, and here is Z mod 2, and over this I have some scheme in characteristic 2, and then maybe I can, if all this works, I can enlarge it to Z mod 4, then perhaps I can enlarge it next to Z mod 8, and so on, and go on extending it till I get a family of such deformations. Each one of them just sits over that set, theoretically just sits over the prime 2, but the amount of nilpotence, the order of nilpotence is growing all the time. And then a miracle takes place if the conditions are right. This miracle is known as the Grothendieck existence theorem, and which suddenly produces a scheme, or whatever that object is, on the completion of Z at 2, which is the inverse limit of all these Z mod 2 to the power n's. So you can begin with any prime, and on the on ZP you can produce a scheme. So in doing this, the important step, there are many steps, but the first step is to enlarge it for a square zero extension, something of this kind. So this problem occurs again and again as the starting point of producing a global deformation. So let us make the simplifying assumption that x0 is smooth over spec A mod I. And this problem need not even be in this affine form. One can more generally think of x0 is over some y0, and y0 sits in y, and this is a square zero extension corresponding to quasi-coherent ideal sheaf J, and what you want is x over y, making this diagram Cartesian and this flat. Even assume smooth, and if this is smooth, then of course this is also smooth by openness of smoothness condition. So for this situation, in my next lecture I am going to analyze this in greater detail. Right now, when it is smooth, the answer is very easy to state, so I will state it. What I will prove next time will go back and prove this, but you should try to prove this from first principles. In any case, a whole lot of it are in the form of exercises in Archon's algebraic geometry. So these statements you should be able to prove from first principles. So here again there are three vector spaces, and any guesses about what are the vector spaces involved? So one of them, automorphisms, is going to be x0 and I tensored T x0 over y0. These are the automorphisms. If there is such a prolongation, then its automorphisms are given by that. The set of all automorphisms is a, I am tired of saying principal set possibly empty. There is a name for such object called pseudo torsor. So, the set of possible extensions will be a pseudo torsor under x0 I tensor T x0 by y. And the obstruction for the existence of such a thing will lie in H2 of x0 I tensor T. The way this result is proved, I'll quickly sketch before I go on to the next step, is locally, because of smoothness, such an extension always exists. This is immediate consequence of the Jacobian criterion for smoothness. So, locally such extensions always exist, and any two such local extensions, you can quickly see that they differ by this, their automorphisms are there. Again, this is a job, and the job has the band I tensor T of x0 by y0. And so, by the same calculation that we did last time, calculation will be the same. So, you can do the whole calculation once again, or just recognize that this is one more example of a job with a certain band, and so the answers are going to be this. Okay, so enough of these examples. Let's return to general theory. But to summarize, the basic step of prolonging under a square zero extension leads to three vector spaces and or three groups. One of them is the automorphism group, one of them is the group under which the set of possible extensions is a pseudo torsor, and the last one is the group in which obstructions lie. So, now let us see what happens next. So, so in general, so since this method is only going to deal with square zero extensions at a time, we can as well assume that our base is local, in fact a complete local ring, because taking such inverse limits will only produce the completion of the local ring. So, for the infinitesimal theory, one can work with a complete Noetherian local ring and let K equal to residue K. To have individual infinitesimal deformations, as parameters we have the category Artin. Well, sometimes it is written like this, sometimes it is written and even though our objects have automorphisms, one can consider the sets of isomorphism classes as the first step. Later we will consider the groupoid and go on to stacks, but if we want schemes we have to consider sets of isomorphism classes. So, what one considers are functors f from such that f of k is a singleton set. This is the starting object which you want to deform, which lives at the residue field of lambda. So, I am not assuming lambda is a domain or anything. So the picture will look something funny. It has one point and here and maybe a number of irreducible components. This is the point K, and on that sits your starting object E. And any element here, A, sits above it, with the close point being the same, and there is an infinitesimal amount of fluff which maps to this, may even map to K vertically. This Artin local ring might sit completely vertically. For example, it could be K epsilon by epsilon square. If I take A equal to this, then as a lambda algebra, it factors via K. So it's completely vertical. So here's a functor which goes from, and this is the starting setup for the Schlesinger theory. Let's relate it to the examples that we studied. So our starting setup may be, there may be an x over, okay, this I think reaches the allowed, no, I don't want this to be hidden. I have only 5 minutes left. So in the case of deformation theory for vector bundles or coherent sheaves, I have certain scheme over spec lambda. I can assume it to be flat, proper, projective, whatever. The more assumptions you put, better results you will get. And there is on xk some E which you want to deform, and so corresponding to any Artin local ring, you take the base change xa and you consider on it all pairs E and I, where E is a vector bundle on xa and I is an isomorphism of E with the restriction of curly E to spec k. So this is a lifting of E to this infinitesimal neighborhood. So to each Artin local ring over lambda with the same residue field, we associate the set of all infinitesimal liftings on that Artin local ring. So this gives a functor of Artin local rings. Given two Artin local rings, one factoring through the other, you can pull back a restriction, a lifting to get another lifting. Yeah, so this is a functor taking values in sets. So Schlesinger's famous paper is called Functors of Artin rings. This is how they arise. He wanted to begin deformation infinitesimally, so he considered Artin local rings and then build up to something larger. So when is this build up possible? And for this, Schlesinger invented 4 conditions. They are known as H1, H2, H3, H4. When these conditions are possible, when these conditions hold, you can go on prolonging and reach something which is the maximal possible, known as the universal deformation. If only H1, H2 and H3 hold, then you end up with a deformation which is known as a hull or a miniversal deformation. That's the end point of the Artin theory. So what are these conditions? These conditions I will state and then I will stop. I will state these conditions in both the set theoretic form which Schlesinger originally had and the groupoid form which Rim in SGA7 recast them into. Later on, Artin in his 1974 paper again recast the conditions of Rim in a more general form, which allows him to reach a conclusion that there is an Artin stack after all. Okay, so here are the Schlesinger conditions. I will state them and then I will stop. This is the Schlesinger condition H1. It says that if I have, okay, so now that the end is in sight, I can take my time. suppose I have two morphisms and this is a small extension. That means if the kernel of this is I, this is the kernel, then I times the maximal ideal of such an extension is known as a small extension. For example, I might have kt mod t to the power 5, and to that I will have map from kt mod t to the power 6, and the kernel of this is t to the power 5, yeah, and the maximal ideal here is t. Maximal ideal here is t. So when I multiply t by t to the power 5, I get t to the power 6, which is 0. So this condition is fulfilled here. Okay. Such extensions are called small extensions. That just makes I into a vector space. Okay. So suppose I have such a diagram in art camera. Suppose there is such a diagram. Then take the fiber product of these. This fiber product consists of one element here and one element here, which map to the same element there, and another component wise operations. One is not used to taking fiber products of rings usually, but in this theory you will see them repeatedly. So the first Schlesinger condition says that the map from f a prime cross a this map should be surjective. These conditions look weird. It looks asymmetric. And why these conditions and why this asymmetry finally became clear in the light of algebraic stacks. So in terms of Artin stacks, it can be explained why this asymmetric condition holds. In fact, it was first remarked by Olson in a paper so do a Google search and find the reference why Schlesinger condition naturally comes from an algebraic stack. Okay. Second condition says all right, I forgot to say what I should have called as the 0th condition, so I will call it H0. Fk is a singleton. All this is the theory of deforming one particular thing. So f of k is a singleton. Okay. So that's why here I am not going to write Fk, simply write product. Is bijective. Now as a result of this condition H2, again a simple exercise for the tutorial, this set f of k epsilon by epsilon square, the k epsilon by epsilon square valued points of f, you know, if f was actually represented by a scheme, if there was really a moduli, then this is going to be the tangent vector space at that point of the moduli. But the condition H2 implies that this is a vector space. So the condition H3 makes sense, therefore. Dimension of the vector space is the third Schlesinger condition, and the fourth condition says if I have small extension a double prime to a, then f of a double prime cross a double prime to f a double prime cross f a double prime is bijective. So here my notation is explained there. Here and here also. So if just the first three conditions are satisfied, then there exists what is known as a hull, which I'll explain next lecture. I run out of time. If all four conditions are fulfilled, then there exists a universal family of deformations of all orders, parameterized by a complete local ring, and that complete local ring is said to pro-represent the deformation functor f. If only H1, H2, H3 are satisfied, then again there is a complete local ring, complete Noetherian local algebra R over lambda with residue field K, and it parameterizes a family of deformations of every order, compatible family of deformations, such that every other deformation can be pulled back from it, all right, except that the map which does the pulling back is not unique. So it has a kind of floppy behavior in the absence of H4. Now these conditions, even though they look weird, they are entirely checkable. So in the beginning I said I have uploaded some notes on conference page, and those notes one by one check these conditions for vector bundles, coherent sheaves, the Cote and Hilbert functor, etc., and show how the hull exists. Okay. Now without going to sets, if one doesn't want to go to sets, the Schlesinger conditions have another formulation, and this is the formulation of a rim where H1 and H2, and I'll explain how H4 looks later, but H1 and H2 take a very simple form. So now I'll have a groupoid. F is a groupoid over I think Norbert explained to you what's a groupoid, didn't you, Norbert? Okay, let's believe he did. And whose isomerism classes produce such a functor f? So given such a groupoid, H1 and H2 combine into a single is an equivalence this is known as the rim Schlesinger condition, slightly stronger than H1 and H2. This implies H1 and H2, but every time you try to check H1 and H2, what you really do is you check this one, so it doesn't involve any extra work. Okay, so when the rim Schlesinger condition is satisfied, we get a Versal family of actual objects, not just isomorphism classes. Okay, so I have run out of time for today, and I'll stop here. What I intend to do tomorrow, and I realize I have planned too much compared to the time available, is finish stating the Schlesinger theorem, and then say how these conditions come from what are known as tangent obstruction theories. We already saw examples of tangent obstruction theories. Tangent obstruction theories come from the cotangent complex, and so the thrust of tomorrow's lecture is to explain the cotangent complex and how it gives tangent deformation theories. The third lecture will begin with whatever Schlesinger's theorem gives, apply Grothendieck existence theorem and arrive at formal Pro families, and then apply Artin approximation theorem to arrive at algebraic families, and then to glue these algebraic families together to produce algebraic spaces which are moduli. So, appears quite a lot. I particularly want to show the use of Artin approximation theorem, because this perhaps is the context in which Artin invented the theorem. So, one should at least show how it can be applied to get moduli spaces. Okay, thank you.